Great pleasure and a moment of pride on behalf of the Department of Electrical Engineering and Material Science and on behalf of the head, Narasimhan, Delhi, to introduce you Dr. Aswani Yella from the Department of Metallurgical Engineering and Material Science. Aswani did her MSc in Chemistry in 2005 from University of Hyderabad. After that, she graduated, that is, completed her PhD from Gutenberg University, Mainz, Germany, under the guidance of Professor Wolfgang Tremel. And that she would do because of the fellowship that she got from Rhineland-Pfalz State Fellowship, which is now called as Mainz Fellowship. People can even apply if interested. During her PhD, she developed new synthetic routes for the synthesis of metal chalcogenide nanostructures, which are used for various optoelectronic applications. Then, in 2010, she joined the group of Professor Michael Ratzel, a very famous personality, the founder of the liquid junction solar cells, a unique configuration of solar cells. And in fact, the cells are known as Ratzel cells at Ecole Polytechnique Federal Lucerne, France. So after completing her postdoctoral studies, where she also got the prestigious EPFL presentations UN, whatever, French teaching award for the year 2011 from the Dean of Faculty of Science at EPFL. Since 2015, she is with us in the department, carrying out research in perovskite materials, not only for applications in solar cells, but also for LEDs and other optoelectronic possibilities. This is a new material. Many of you who work in photovoltaics might know perovskite, the ABO3 type of material, particularly has broken records of the rate at which the efficiency has risen over the time span compared to silicon. So it took 25-30 years for silicon to rise from 2% to 25%, but it took only 5 to 6 years for perovskites to rise from 0% to about 20-22%. There are issues there, but I'm sure people like Aswani are able to solve those issues and we will have much cheaper photovoltaic energy. People can Aswani to give that.
Thank you very much, Professor Dasane, and thanks to also IRCC for giving me this award. And my talk is based on hybrid perovskites and their applications for photovoltaics and beyond photovoltaics, if we can use them for any other applications that are actually present. So this is the outline of my talk. I'll just give you a brief introduction about why we are looking at the perovskite solar cells, and then I'll talk about the perovskite solar cells, and then the hybrid perovskites for use in moisture to electricity conversion that we have newly developed, and finally the conclusions. But we have actually limited amount of oil that is present, and then the estimated energy that we are actually going to use is around 30 terawatts. I mean, that will be keep on increasing. Estimated amount is 30 terawatts. The current consumption is around 20 terawatts of energy that we are using. And not only that, we have limited amount of oil, but we also have the emission of carbon dioxide that is actually coming out from all these fossil fuels. So because of which the temperature rise is happening and global warming and everything. So if we think of some non-carbon based energy sources, then the nuclear energy is the first one that we can think of. But the nuclear energy is something that is not a safe form of energy. So I mean, in 1986, it has been predicted that this is something that is as safe as a chocolate factory, but of course, it is not as safe as a chocolate factory. We know all these explosions that has happened in Chernobyl and in Fukushima in 2011. So nuclear energy is not an option to go for. So we have to obviously go for some forms of renewable energy. So there are actually many forms of renewable energies that are actually present. So that is wind energy, tide or ocean currents, geothermal, biomass or hydroelectric forms of energy. But the energy that is, that can be extracted from all these different forms of energy is actually very little in comparison to what we are actually consuming right now. So the energy consumption the current world consumption is around 20 terawatts, but you can see that the maximum amount is something that is actually very little in all these forms of energy. So the one form of energy that can be utilized to produce actually that much amount of energy that is needed for the world consumption is actually the solar energy, because solar energy, the amount of energy that is falling onto the earth is approximately 120,000 terawatts, And the land, I mean, for producing 20 terawatt production, we only need the squared areas that are shown on this map, on the world map. If we have actually like 15% solar cells installed on all these areas that are actually shown, we should be able to cover the 20 terawatt production that is needed for the world world energy consumption. So there are actually many ways to make actually these photovoltaic devices, or using solar energy to convert into electricity, like thin film solar cells, crystalline silicon solar cells, or the concentrated photovoltaic cells, and each of them has got their own advantages and disadvantages, of course. But of course, the silicon solar cells is actually the one that leads the solar race. I mean, wherever you see, the main solar cells that you see are basically the conventional silicon solar cells. And the other technologies, the thin film solar cells or the organic solar cells or any other solar cells that you see, they have not come to the rooftops yet. So these are something that has to be, I mean, this is prepared by using actually many vacuum processing techniques. The silicon feedstock is actually made into an ingot, and then they are sliced into the wafers, then the cells are fabricated, and then the encapsulation, and then finally we end up getting these photovoltaic systems that we see in IIT. We have many installations that are actually present. They have actually very high efficiencies. I mean, the single crystalline silicon solar cells have around 27% efficiencies, but whereas the polycrystalline has around 20%. And they have also longer lifetime of around 25 years of the lifetime minimum. And they're slightly expensive in terms of the production, because they use most of the high vacuum techniques. That's the reason why they are actually slightly expensive. And the major problem is actually the long return in the investment. So if we wanted to install in our homes, then what people think of is that if I do this investment, and the payback time is approximately 4 to 5 years, minimum payback time. But if we can reduce the cost of the production, cost of these solar cells, then many people would be interested to have their homes lighted up with the solar cells. So to have these costs that are, if we have to bring these costs down, then we need to actually reduce, reduce the cost of the material deposition cost. We can find alternate materials, or we have to actually reduce the thickness of the films silicon films that we are actually using. So if you have to reduce the film thickness, then we need to go for some light trapping methods so that we can actually reduce the film thickness, or use some concentrators. But the best way to do is to actually use something that is actually called as the multi-junction solar cells. So in this kind of solar cells, we can still use actually the silicon solar cells, but increase the efficiency by making many junctions that are actually present. So in a conventional silicon solar cells, what we do is normally take only silicon, and then we take silicon has a band gap of 1.1 electron volts. So all the photons that has energy that is greater than 1.1 electron volts will be taken up by the silicon solar cell. But if we make actually a kind of multi-junction solar cell, then the multi-junction solar cells has got actually different junctions, having different absorbers that are present. So since we know that the visible light has got many different frequencies of frequency of the light that is present. So if we combine all these different absorber materials, so the first absorber will be taking up the blue light, then the second one will be taking up the green, then the third absorber will be taking up the red part of the light that is actually, of the visible light that is actually present. So this way we should be able to capture much more of the sunlight, and we should be able to get much higher efficiencies in comparison to what the silicon solar cells can offer. Because for the same area of the device, we could actually now increase the efficiency of the device, and we could get actually, and we should also have the less production cost for these. So the multi-junction solar cells in principle are actually proposed to be actually very cheap. But because of all the this is an example of one of the multi-junction solar cell. Because of all the layers that are involved, these are something that are much more costlier than the conventional silicon solar cells. So if you can think of, this is approximately $5,000 per meter square of the cells for 30. The efficiency is of course higher than the silicon solar cells. So instead of having a 17%, now we can go up to 37% of the efficiencies. But these are even more costlier than that. But if we can actually make multi-junction solar cells with the multi-junction being a material which is actually cheaper in cost, then we could actually reduce the cost of these solar cells drastically. So right now, if you are looking at the current day silicon solar cells, around 19% efficiencies, we have rupees 60 per watt. But if we could make actually a silicon and then a perovskite, which is the material that we are actually using, if we can make a multi-junction solar cells using these two, then we could reduce this to 48 rupees per watt. The cost of the solar cell can be reduced to 40, because the cost of this perovskite material is something that is very cheap. So we could in principle reduce the cost of the solar cells also to be per watt as rupees 48 per watt, or in terms of meter square it will be around 12,000 rupees per meter square. If we can increase, instead of having a 25% efficient cell, if we could increase to 30% efficient cell, then the cost will drastically cut down to 7,000 per meter square of the silicon, of the solar cell that we are actually using. So for this we need to combine these two technologies, that is actually one of the low cost technology and then a silicon solar cell, so that we can increase the efficiency to 30%, and finally we can reduce the cost of the solar cells. So this is actually one of the proposed thing that we are actually working on, that is actually combining the silicon solar cells with the class of solar cells, that is the perovskite solar cells that we are working on. So if you look at this is actually called as the NREL chart. The National Renewable Energy Laboratory in the US actually certifies all the solar cells that are actually, I mean, any kind of a solar cell technology, they actually certify the highest efficient devices. So you can see the timeline of different these are the different kind of solar cell technologies that have been developed over the course of years. From 1975 they started till now, what is the progress that has been taken place. So you can see the highest efficiencies that are reported are around 47% are for the multi-junction solar cells, multi-junction with the concentrator that is actually used, not the sun intensity that we are seeing, but we are actually increasing the intensity to 143 times higher intensity, then we can get these higher efficiencies. But to make the multi-junction solar cells much more cheaper, we need to look after the cheaper materials. So one such technology is actually this yellow dots with around this thing. So this technology has started from 2012, and you can see that no other technology in this map has got a steep rise than this one, as Professor Aswani also has mentioned. So this has increased from roughly 8% in 2012 to something like around 25% right now. And the tandem solar cells that are made, the perovskite silicon tandem solar cells, right now the efficiency that has been obtained is actually 28%. So this particular material has got actually a structure that looks like this, that is a crystal, I mean the name perovskite has come from the crystal structure, which has an AbO3 kind of structure, and the perovskite is, the name has come from the scientist who has developed this structure, the Perovsky. And the material that we are actually using is actually called as methylammonium lead iodide, which is actually an organic inorganic hybrid material. So the organic part is actually this methylammonium part, and the inorganic part is basically the lead iodide part. So this material has got, the reason for this very steep increase in the efficiency is because it has got very interesting properties. Like it has got a very high optical absorption coefficient, which means that we only need actually 300 nanometers of the film to absorb all the sunlight. Not all the sunlight, but the visible part of the sunlight we can absorb by using only 300 nanometers of the film. And it has got also excellent charge carrier transport. Like it has got electron hole diffusion lengths are very long, and the carrier mobility is also very high. So because of these excellent charge carrier transport properties, we have actually very high VOC that is obtained for these devices, which is approximately 1.1 volt for a band gap of 1.5 electron volts. So, but of course, these are actually the good things of this material. But since this is a material that is very easy to make, we can make it at 60 degrees centigrade temperature. Unlike the case of the silicon solar cells, where you need very high temperatures to crystallize, this material can be crystallized at as low as 60 degrees centigrade temperature. But this is a material that is easy to, any material that is easy to make is also something that is easy to break. So this material is something that is not stable with the temperature. If you go slightly higher temperatures than 60 degrees centigrade, it degrades. And especially it degrades even more in the presence of humidity. And humidity is something that is actually very high in Mumbai conditions, because of which this material is practically not very useful in Mumbai condition or places where we have very high humidities. So this is actually how the film of a methylammonium lead iodide looks like when we freshly prepare it. And this is a methylammonium lead bromide film, which how it looks like when we freshly prepare. But when we keep in hot and humid Mumbai conditions, within a few days, this film actually turns to like this, and this film will turn like this, something like this. Whereas the average humidity in Mumbai is around 76%. The relative humidity is very high, that this material actually decomposes to lead iodide. So the methylammonium iodide part that is present is something that decomposes, and then we end up getting actually the lead iodide part. So we are mainly interested in actually increasing the stability and then make them useful for making the silicon and then the perovskites or tandem solar cells, so that we can use them for real life applications. So whenever we are preparing this methylammonium lead iodide that is present, we normally take it as a 1-to-1 ratio of these two, that is methylammonium bromide and then the lead bromide, and then we end up getting this methylammonium lead bromide that is present. But Instead, if we take actually, what we thought was that if we take actually excess of this methyl ammonium bromide, we could somehow protect this methyl ammonium lead iodide, and then we can make them much more stable. I mean, we can probably increase the stability of these devices. So when we increase the methyl ammonium bromide concentration, what we found out is that we don't get this colored phase that is actually present, but instead what we ended up getting is something that is transparent. I mean, the white that you are seeing is basically the mesoporous titania, but in principle this is something that is completely transparent. We don't see any absorption that is coming up from the visible light. And when, I mean, serendipitously what we found out was that when we take this film and then if we go outside of our lab, I mean, inside of our lab the humidity is something that is actually very low, something like around 40%, but when we went outside the lab, the film has turned its color to something that is actually very dark, more or less similar to the methyl ammonium bromide, lead bromide that is actually present initially, whatever that we have prepared. So that means that, and when we came back to the lab, the film is something that is turning back to its original low, I mean, this transparent phase that is actually present. So we have done a systematic study by actually taking this 4 times excess methyl ammonium bromide and also 1:1 ratio. And then the 1:1 ratio film doesn't really change much at 10% or 60% RH, but if we keep it at 80% RH, then the film has slightly degraded. Because the methyl ammonium iodide is something that is reacting with the water. But when we are taking excess of the methyl ammonium bromide, the film actually at 80% RH is something that is more or less similar to the case of the 3-dimensional this perovskite that is actually forming. So that means that there is actually something that is some reaction that is going on with the water, or some transformation that is actually taking place. So we have, I mean, okay, the same thing in the UVB spectra also you should be able to see when you take the spectra. So at 40% RH, what we saw was that this film is something that is completely transparent and we don't see any absorption coming up. But when the humidity is higher, we ended up seeing the visible light absorption that is coming up from the methyl ammonium bromide films. So we did actually, to find out what it is forming at low humid conditions, we did the X-ray diffraction studies on this one, and then what we found out was that at low humid conditions we are not forming actually this 3-dimensional perovskite that is actually something like this, but instead we ended up forming a 0-dimensional perovskite that looks like this, where the lead iodide octahedra are not connected to each other. So this methyl ammonium, the MA4, this has a formula of something that is Ma4PbBr6. This actually is converting when we are putting it under humid conditions. Then the methyl ammonium bromide is reacting with the humidity and then forming a 3-dimensional perovskite that looks like this. That is also confirmed from the X-ray diffraction pattern, where at 60% RH we have actually the complete transformation to the 3-dimensional perovskite, which is actually the MaPbBr3 that is formed. So this process is something that is completely reversible. We could go back with the humidity from 40% to 80% and we could measure so many cycles, and the process is something that can be completely transformed into one another. That means the 0-dimensional perovskite changes to the 3-dimensional and back and forth. And this is something that is also very stable at 60% RH, because the material is forming only at 60% RH. So that's the reason why this is very highly stable. And also at 60 degrees centigrade temperature, we have studied at 60% RH, and still there is no noticeable difference that is actually observed for this film. We also kept it under the light because there is also some degradation that has been observed in the previous literature for 3-dimensional perovskite. But in the case of the 0-dimensional perovskite, we didn't observe any kind of the degradation in the light also. And this material has got some interesting properties with respect to the photoluminescence. So the 0-dimensional perovskite has shown this red one that is actually present is actually the 0-dimensional perovskite has got shown a huge photoluminescence that is present. Whereas if we are increasing the humidity, then the luminescence has actually reduced, because probably the methyl ammonium ions that are present is actually helping with the recombination process, and that's the reason why the photoluminescence is actually reduced. So we could actually see this change in the photoluminescence by using actually by using imaging, luminescence imaging. So at low humid conditions, you can see that the particles are all round in shape and they are very highly luminescent. I mean, the brighter image means that they are actually very highly luminescent. So when we increase the humidity of this on these particles, you can see that around 60% humidity, the particles started to change their shape from round shape to actually a cubic form of, I mean, the square shaped particles are actually, this is a 2-dimensional one, so that's why you see it as a square, but in principle these are converting into cubic shaped particles. And the intensity also gradually reduced when we are increasing the humidity in this case. And this is also something that is completely reversible. We can also visualize the reversibility in the microscope, where we can see that again the square shaped particles turn back to the shapeless particles that are actually present. So this 0-dimensional to 3-dimensional perovskite conversion is something that is completely reversible transformation that is taking place. So we made some devices using this 0-dimensional perovskite, and we could actually obtain efficiencies much better than the 3-dimensional MAPB-BR3 that is present, and we could get efficiencies close to 5% efficiency at 60% RH. At low humid conditions, the film is something that is transparent, that looks like this, but under the high humid conditions, it turns to something that is colored, and then we get the photovoltaic efficiencies. See, at low humid conditions, the device doesn't work. It only results in 0.25% efficiencies, whereas under the high humid conditions, we end up getting around 5% efficiencies that are present. So we studied the stability of these devices at 60% RH. Under these conditions, actually the MAPB-BR3 devices have degraded continuously, whereas the perovskite, the 0-dimensional perovskite device that we have made is something that is stable for around 250. I mean, we only studied until 250 hours, but it is quite stable for 250 hours that is actually present. But the films never degraded even afterwards also. Since this is something that is actually a reversible transformation, so we could actually also do this for like smart windows, where we could actually change the humidity, and then we could actually see that the efficiency is actually going up and down. So when we reduce the humidity, the efficiency reduces. When we increase the humidity, the efficiency also increases for the device that is present. So since this is something that is actually, since there is a transformation that is taking place, and then the methyl ammonium bromide ions are actually moving, what we thought is that we wanted to check the ionic conductivity of this material, and then we made some devices using simple 2 FTO glasses, and then deposited the material in between, that is Ma4PbBr6. So interestingly, when we measured the IV curve at 2 different humidities, this is all done in the dark. There is no light that is there is no sunlight that is involved. When we measured them in the dark at 2 different humidities, you can see that there is actually an open circuit potential. I mean, the minimum of this current is not observed at 0 volts now, but the minimum of the current is observed at a certain voltage. That means that there is actually a certain potential that is developed in these devices in the dark conditions when we are using 65% RH. So that means that, I mean, we are actually generating some amount of energy in the dark, so some amount of electrical energy in the dark. So we have measured actually the open circuit voltage. We saw that at 11% humidity, there is no voltage that is generated, but as soon as we switched it to 65% RH, there is actually a certain voltage that is generated from this device. This is measured only all in the dark. So the open circuit potential that we are seeing is coming up from the material itself. And there is also a current that is generated. The current is still very low. There is only 0.1 milliampere per centimeter square, but still we could see some current that is generated as well as some voltage that is actually generated from the device. Yeah, this is actually the moisture. No, when we measured the device, we actually did, this is actually the measurement that IV curve that we have measured. No, normally it should come at 0 volts, because unless there is an open circuit potential that is generated from the device, the minimum in the current should be at the 0 volts. Because whenever we are applying certain voltage, then the current there should be some current that is flowing through. Yes, at the open circuit potential, the current is the one that is actually 0 or very minimal. So we have also measured systematically at different voltages, different humidities, like at 10% RH, 33%, and so on, different RH, what is the voltage that is generated. And then we saw that at around 65% RH, the voltage is something that is actually maximum that is obtained, because this is the point where around 60% RH is the point where we have the transformation that is taking place, and the maximum number of methyl ammonium iodides are actually released. So that's the reason why the voltage is something that is maximum at this point. So this is also something that is completely reversible. So we could also go from the low humid state to the high humid state, and then you can completely reverse it back and forth. And we also measured the current. The current is something that is also maximum around 65% RH, because this is the point where we have more number of ions that are generated, and the more ions are actually resulting in ionic conductivity in this material, and that's the reason why we are seeing this current that is actually generated around 65% RH. And we also carried out the XRD, which also shows the transformation from the 0-dimensional perovskite to the 3-dimensional perovskite, which is the transformation that is completely reversible. So we have also calculated the power that is generated. The power that is generated is around 400 milliwatt per meter square. This is still a very low amount of the power that is generated, but we are working on improving the power density of these devices that is actually present. So when we connected, we have made 6 such kind of devices, and then we have connected them in series. So when we connected them in series, you can see that the voltage has actually added up, and then we could get the voltage of around 3 volts for this device. And when we connected them in parallel, the current has added up, and then we could get around 0.6 milliampere per centimeter square. And the voltage for, if we connect these two devices, then we could get actually voltage that is sequentially increased for all the 6 devices. So this is 2 connected, 3 connected, 4, 5, and 6 connected devices. So all the 6 devices. So we could also light up some small LED that is actually present. Okay, its quick time is not available. Yeah, it's not available. Okay, but we could actually show that the light up. I mean, using this is all done. I mean, there is no light that is actually involved. We can actually see that the LED can be lighted up just by the moisture. So we are basically converting moisture to electricity, moisture energy to the electricity conversion. So this is something that may not be going to the rooftops, but of course these can be used for something like a niche applications like tablet or smartphone cases or electrochromic sunglasses or some bags that are actually present, because moisture is present everywhere, and then we can use the energy from the moisture to convert into the electrical energy. So this is something that can be applied for a niche applications that are actually present. So in conclusion, I have shown this reversible dimensionality tuning of the humidity from the 0-dimensional perovskites to the 3-dimensional perovskite, and we have used this approach for making actually smart solar cells, which can convert with the humidity to the efficient devices to high efficient devices to low efficient devices. So in principle, we can use them for a self-forward humidity sensor, because based on the humidity, we should be able to see we should be able to find out whether there is a color change or not. And then we have also showed this new concept of moisture to electricity conversion using these ionic conductors that are actually present. That is perovskite based materials that are actually present. So I would like to thank all. I mean, this is something that is not possible without actually my PhD students, which are actually listed over here. And all the work that is actually shown is actually done by my student Sumit Kumar Sharma. And I want to also thank the collaborators and the department collaborators and collaborators from other departments and other universities that are actually present, and also the current and the past MTech students. And of course, thanks also to the funding from the IIT seed grant, which has helped me to start up initially, and then the grants from the DST and then MNRE, that is the NCPRE center. And then also I would like to thank Professor Balaji for giving me some extra support for purchasing actually the glove box. So that has been generously funded by Professor Balaji later on, is apart from the seed grant. So thank you all for